I can't help smirking through the silence. It's just in my nature. Hello, welcome to a video. I'm here. Jez is here.
Hello.
And Jez is like my programming granddad. I need to start off by saying the funny thing that I did yesterday, which is so for the viewer, this will be the next video or the one after that. I'm not going to upload it until after this one. But last night I recorded a video. I'm going to clarify that. So the thing I recorded last night will be after this video that we're recording now on my feed. And anyway, last night I decided that I'd had enough of the just all the stuff in the discourse that's happening in the programming world, and I was just going to write a nice simple little game. Mm-hmm. And so I did that, and I think it was okay. Like, obviously I didn't finish the game. I got halfway through, and as my colleague said to me, in my next video I'll get another quarter of the way through and it'll probably proceed from there.
That's right, like Zeno's arrow. Yes. Proceeding towards.
So so it's a great video. Everyone should watch it when it comes out. It's only 2.25 hours long. And,
oh my God, man.
and like at the end of it, there are some boxes drawn on the screen.
Great.
Yeah. Anyway, the game that I want to implement, I had to do a lot of Googling to find out what it's called. There's a game you may have seen where balls bounce around the screen, and then you like chop the screen into bits and try and isolate the balls from each other and then from areas that have no balls in, and then those bits get plugged in. Does that ring any bells? I
want to say this is like a really early arcade game, right? It's
yeah.
Tracks or something like that.
Ah, well, that's interesting. So I found something that is like a precursor to this game, which I think was called Quux.
Ooh.
And in Quux, you control a dot and you like draw a rectangle, and you have to get back to the edge before one of the balls hits you. And you gradually chomp off more bits of the screen. But the game that I found that's closest to what I'm imagining writing is called Jez Ball. Jezz Ball. That's not the funny bit.
Okay.
So I thought, well, that's ideal. I like Jez. I like the idea of a tribute to Jez as the name of my game. I can't just call it Jez Ball. There's already something called Jez Ball. So I'd been reading your toots about hockey this week.
Right.
And I thought, well, Jez is into hockey, so I'm going to call it Jez Puck, because pucks are a thing that happens in hockey. I went ahead, I made the Git repo, I set the title, I recorded the video, I went to bed, and I got up in the morning and thought, that's the wrong hockey.
I got the wrong hockey.
And that would be fine if Jez Puck was a good name, but Jez Puck is an awful name.
Yes. Okay.
So, I'm really on the lookout for a new name for this game. But yeah, that happened. Anyway, so that'll be the next video.
I'll have to look forward to that. That's lovely.
You can watch it on like 7 times speed or something, and then it'll be a reasonable length.
What I often do, Andy, is pop you on while I'm working.
Yeah.
And then you're my kind of like co-worker.
I think people do that.
And you don't stop, so I don't stop. It's like,
I see.
And you come out at the end and you go, oh my God, it's dark outside, Christ.
I mean, I'm recording it generally after midnight, so yeah.
Yes.
It's after when you should have stopped already.
Oh, yes. Generally have.
Okay, so, viewer, if this is the first Andy and Jez video you've watched, you think it's like an entertaining podcast, but it's not. It's quite a dull coding video. So what we are doing is we are in the middle of implementing an implementation of gunzip. which we've called, which has got a much better name. We've called our implementation GG unzip for like good game unzip, right? Like the kids, that's what the kids say. And I guess we should look at the code. Should we look at the code?
We should look at the code because I did fiddle with it a little bit after we.
All right. Well, let's try and get our heads back into the code. Sorry. Let's get our heads back into the code by you talking us through.
Yeah. So, as we've said before, and I'm really getting used to this now because I've read that RFC so many times. Gzip compresses like one thing. It's not like a multi-file compression. It compresses one thing, which is why often, of course, you tar things up into one big lump and then you compress them.
Yes, you do.
And the compression algorithm it uses is a thing called deflate. And deflate works in chunks. And each chunk has a little bit of information at the beginning and then some compressed data. And then you get another chunk and you go on through until you've all done. And then the gzip file itself puts a little header and footer on that compressed data stream.
Right.
Each chunk of compressed data can be compressed in one of three different ways. And we have done one of those ways, which is uncompressed.
Right.
So you can just copy. So I think it's in deflate. Yes, I think it's in deflate stream. So here we are. So you had it there. So once we've read the gzip header, which tells you things like the original file name and some metadata about like the file time and curiously, the file system it was running on when you compressed it.
Order. And
some other bits and bobs like that. Then you go into the compressed stream, and at the beginning is a little header byte that tells you what the compression scheme of this chunk is. And that's 2 bits that you read there. And that's what we've got here. So we're reading 2 bits from our bit stream, and then you switch on that. So if it's 0, 0, right, the stream is uncompressed.
I was reading this as like hex. I was like, what's this? How do you get to a B in hex from 2 bits? But I see that this is binary.
And this is 0. Binary. And so that's an uncompressed block, and you can just read the whole thing, essentially. Right, it has a length, a 16-bit length, and you get it twice, so you get it in kind of inverted.
Which is some kind of checksum?
That might not be right. I think we might have an error there. But anyway, it doesn't matter.
We're not lenning. Should we be...
Oh, no. Yeah, sorry. One is a bit inverted thing of others. So, yes, not equal to not len. So we bit inverted it, bit flipped it.
We are doing, unary. This is a bitwise operation, is it, on this?
Yes.
On the U16?
Yes. Sorry, I didn't see that properly. So that's... And then you can just read the whole chunk and then copy that out. So that's what we've got there. We read.
So we read out the length.
That
we
many
read
bytes.
out this kind of check of the length. We compare it to make sure. Then we do. We're reading from this thing called F, and so take tells it like limit it to that many bytes.
Get that many bytes.
Len, and then we
copy them directly to the output.
Right. So this body thing is like the result of saying only take this many bytes from F. We've got this body.
Yes.
Copy from that into OF, which is our output file, which we were passed in.
Yes.
Cool. All right. So we've read an uncompressed block.
So here, what we did last time was work on biterator there, which is an iterate. So normal iterators will read over characters or bytes or words or something. But for this, not just here, but elsewhere, we need to read a bit at a time, one single bit. So we put, we've constructed this biterator. See what we did there?
Which
around
an iterator.
Our byte stream.
It is an iterator.
It is an iterator.
But do we care do we use the fact that it's an iterator anymore? Or? because we
So when we finished the video, we'd written it as an iterator because obviously that's quite an easy trait to implement. And so we could verify the behavior quite easily. And then what I did afterwards was then kind of extend that out with methods that were more like the read interface.
Right.
So I can say, I want 1 bit, or I want 3 bits, or whatever. And that does some error management for me here. And it flips it into a result and does a few little bits and bobs for me. But I'm using our iterator to implement that. Nice. There are more efficient ways of doing this, but it doesn't really matter here.
Yeah, so I see that readbit is using next, which is the iterator, and then readbits is using readbit. So we could, if it gets slow, we could do it some other way.
Yes, but we're not particularly worried about that. In one of those, I keep seeing articles about gunzip now, and there are lots of people who are very proud of how they've made these sort of super efficient things.
Right.
But which, if you are using this in a network stack or something, probably relevant.
Absolutely.
But if you're just unzipping things on the command line,
not relevant.
Probably not.
Yeah, I mean, this is now, it's like, I'm sure, like any kind of kernel-based web server will be implementing this algorithm, or rather gzip algorithm, because almost everything gets sent over the network. It makes sense to gzip it these days.
Yes, but actually a lot of things now use other more efficient algorithms.
Right.
For Brotli,
right. But gzip is like the kind of baseline of everything.
In theory,
right?
Yes.
Okay, and then just a reminder of what we did last time. We did what you would do if you wanted to get the bits of a thing one at a time.
Yes. So we if we haven't got a byte in hand, we pull off the byte and then we just peel off each bit until we've taken 8 of them, and that's what's happening at the bottom there. Just a bit count.
And we return a U8 which is always either 0 or 1.
Yes, because there is no bit type in Rust, because that would be mad.
Boolean, but our Boolean is actually just a U8 that is either 0 or 1.
Yes, but that would be a lie.
It would be a lie.
Because it's not a Boolean.
I like what we've done. And we have tests. So my next question is going to be, I know that we did some fiddling around with this and we actually uncompressed a real file.
Yes.
Not a real file.
We have it there in example.
By gzip, but a real file.
No.
But
we constructed the file because, curiously, I don't think gzip will put uncompressed data into a file.
It would just be brilliant,
try and compress it,
wouldn't it, to ask gzip to do that?
There are, I'm fairly sure, I'm relatively confident about this. There are capabilities in the deflate algorithm that gzip does not expose.
For zipping or unzipping?
For zipping.
Hopefully it does all the unzipping, right?
The unzip is easier.
Yeah, that's why we're doing it.
Yeah. So when you gzip, you can say like -1 or -9 if you want it to compress more or compress quicker. And I think what you're doing there is tuning a parameter in. So the compression that it uses is a combination of a Huffman encoding, which is like a run length encoding, essentially. It's a run length encoding. No, it isn't. Sorry, it's a lookup encoding. So it's a frequency encoding. So things that occur more frequently. The things which occur more frequently are encoded into fewer bits.
Now, you sent me a podcast about this, which I
did.
duly listened to. It was awesome. And now I feel like I know what deflate. How deflate.
Oh, yeah, he just was super clever and he just came up with it and Claude Shannon couldn't. It's like, what? Anyway. Yeah. And then it combines that with a lempel-ziv encoding, which is if you get like a repeated sequence, in the output, it says, go back this far and just use that many bytes again. So it's an offset and length.
Which is beautifully simple.
And when you do that -1 or -9, it's looking harder or not as hard to find those sequences.
Okay, just for the second part.
Yes.
Right.
But there's a whole, obviously, between -1 and -9, there are, -1 and -9, there's -2 and -3 and -4.
Yeah. I thought you were going to ask me to count how many there are, which is beyond my skill.
No. Again, I stumbled across an article the other day about somebody who was tuning those increments on their gzip encoder algorithm because you don't get a linear change in behavior in the kind of the standard implementation. You get this kind of curve.
Well,
right. So the compression is the point is the compression is much harder. And for the decompression, you don't have to worry about that because it's all just the state within it.
So decompression is just a matter of reading a recipe and executing it, right? Whereas compression is a matter of inventing, this is my way of thinking about it, inventing a way to make the file smaller in some sense.
Essentially, yes. You're doing
stuff to compress.
You're doing analysis on the file.
Yeah.
To work out the best way to compress it, and then you compress it. But once you've done that, the information that's encoded within the compression scheme. And so when you come to decompress, you just read it back out.
So we're doing right now, I mean, if we really enjoy this, we can do the compression bit and we can do some original research on how to make the best deflated file.
Okay, let's not get ahead of ourselves.
But first, we're going to do the easy bit.
But first, so we have done, like I said, there are 3 ways that a block in the compressed stream can be encoded. And we have done, and we did this very early on because it's quite easy, the uncompressed version.
Yes.
The other 2 are this combination of Huffman and Lempel-Ziv encoding with a known Huffman tree. Right. So like a pre-canned one.
Yep.
And the third one is encodes the Huffman tree as part of the block and then decompresses the rest of the block using the Huffman tree it's just told you about.
So this tree is like a dictionary of like patterns we've found that repeats in the thing.
But because it includes this Lempel-Ziv offset and length lookup, what I would like to do this evening is just to do a circular buffer or some kind of buffer that we can look back into.
Right.
So when we're writing, at the moment, our output, we just write directly to a file, but we're going to have to write either through or simultaneously into a sliding 32K window.
Right.
So that when we come to do the compression scheme, we can look back and say, oh, there's a thing. There's a thing. Because we need kind of all the bits in place.
And 32K is like the maximum that you're allowed to look back.
Yes, because deflate is old. Yes. And 32K was quite a lot.
But also,
at the time.
There's something very cool about that. Like, I don't think it would be as ubiquitous, gzip, if it weren't like low spec. So there's something cool about using old technology that means it can be used everywhere. Maybe.
Well, I think the point about the Huffman encoding is, and this was the key thing in that podcast, which
I'll link to if I remember, by the way.
Yes, it was a recent episode of Co-Recursive. Was that Huffman demonstrated, I haven't looked this up to kind of see the maths, but he showed that the schemes that his method came up with were optimal.
Yeah. It's mad.
Yeah.
So I think it's specifically optimal in the sense that they, like, you use as few bits, like the most common things to look up, use fewer bits to look up, right?
Yes, but he did the math to show why the particular encoding that you came up with for a particular piece of data was optimal. I think that was a breakthrough. I think the general principle was known, but his method.
It's incredibly cool.
I think that's right.
It's incredibly cool.
Yes.
So, and now one question just before we start implementing things, because I think that's a cool thing for us to do. Where are we at with testing? Like, do we have a system test that checks that the thing we saw working on the command line actually works? And if not, can we have one?
Have a look in main. I think that's
a load of commented out stuff.
I don't think we have anything that kind of runs the application and compares against a known good external file. We've got lots of stuff internally. This stuff we've commented out is
I'd love to take
from when we
were
getting clever.
Yeah, I'd like to take some of this stuff we commented out and turn that into a test that just says, when I feed in this known zip file, it comes out like...
Yes, but this is not it.
Right,
This was us creating, like this is left over from us creating our test file because we...
Yeah.
But using somebody else's.
We are going to want that, right? Because we couldn't get Jez to create something simple enough yet.
Yes.
But I think we're going to want that, right? In order to do
examples, we have uncompressed A there is
just an A.
Uncompressed A.gzip .gz is a proper gzip file with an uncompressed block containing the letter A. So we could use that as our system file, as our system test.
Yes, cool. Okay, hang on. GZCat, that is a thing. Yeah, okay. So this one.
Yeah. Ooh.
What? Oh, well, it's called ZCat, isn't it? Yeah, and if you look very carefully, viewer, you can see there's an A over here that came out from that.
That's right.
All right. So, yeah. So do we... I'm thinking we could write effectively a unit test. Like, we don't need to use real files. Or we could just use that real file. What do you think? Should we just use the real files?
Well, I think we have got that somewhere.
Do you?
But I can't remember where. See, this is us testing particular bits of the block. And we've got separate tests for the header, the gzip header. And we've got tests for the bits of the block.
Yeah, so these are doing inflate stream. Is that a full stream? What does inflate stream do?
This is a properly put together deflate stream containing two separate uncompressed blocks.
Fine. All right. Okay, we've got
the single byte in one. So we are. Yeah. All the individual bits are there. Yes.
Fine. I'm happy. All right. I'll stop banging on about that. Okay. So, where is this going to fit? So right now we've got...
I think it's going to fit, and it's at the moment it's an entirely standalone piece of work.
Because
so it's going to be a sort of a sliding window or a circular buffer or something like that. And then what we want to do is that's going to take our output stream as a parameter, perhaps, and either it's going to write through to it or it's going to I don't know quite how it's going to put together. But as we write the output, we want to be transparently buffering up 32K worth that we can then look back into and extract, take X bytes.
So we have...
That's what we need.
We have this function called gunzip, and it takes in a file to read and a file to write. And then it writes to OF. And these are all files, and I feel like they should be...
No, but they're files here, but we're passing them down as reads and writes.
So inflate stream takes a write. So that's good. So I feel like we just want to slot in somewhere like here, like wrap it up in our buffer in some way.
Yes. But it needs to happen inside inflate stream because the decompressor needs to have access to that. We're not going to put it on here,
right.
But that's not important right now. We just need that capability.
I see what you mean. Yeah, so we need a way of saying in here so we have access to it. Wrap up my thing which is a write with another thing which is also a write, but which gives me other stuff as well. Fine.
Yes.
What are we going to call this thing?
Well, I've been saying circular buffer because I'm leaping immediately to implementation, but it's a sliding window, or is it the look back buffer?
It's a
something like
is
that.
Look back. There's such a thing as look ahead. Is there such a thing as look back?
Why not?
Look back buffer.
Yeah.
Fine. Let's go ahead and say it's a struct for now. And let us include it in
has your NeoVim there got much more wordy suddenly? Or have
I don't know. Like
that bit that it popped up where it said this is not part of any project yet and things.
Right,
I'm not sure I've noticed it doing that before. Is it just getting chattier?
No, I don't think it's any chattier, but probably sometimes the whole screen gets covered in grim text and it makes me sad. So I think it just did that.
Sorry, I realised I should apologise for my T-shirt.
What's wrong with your T-shirt?
Do you not? This is a decomp T-shirt.
Decomp language. Don't apologise. D is a perfectly respectable programming language, which no one uses and isn't as good as Rust.
well,
but it tries to do what Rust did, which is replace C++ with something better using all the lessons we learned from C++. Tell me I'm wrong.
Without wishing to be rude to anyone, I'm not sure it necessarily learned all the lessons.
Yeah, I agree. Or it learned the wrong lessons even. I mean, Java did that too, so you can't really blame anyone. Java did it worse.
Yes, Java is a thing of its own. Russell, of course, was always very. It was pains to separate the JVM from the Java language.
Yeah. Well, actually, the JVM was a little bit focused on the Java language, but yeah.
Well, of course, initially, but it's quite a powerful beast.
Yeah, I mean, it's cool. It's cool, but it's not as cool as compiling to an executable that just does your thing without. Anyway, but you know your D, right? You're one of the world's leading D experts.
Really. I am not, and my D programming friends would be horrified to hear you say that. I have done some D. I did some work actually on a range library.
Right.
So D, I don't know, this might be before your time, but I don't know, 12 years ago, maybe longer ago than that. Andrei Alexandrescu gave a talk at the ACU conference on ranges.
Yeah,
you were there for that.
It was awesome. It was an awesome talk.
It was.
One of the sad things for me about D is the amount of talent that has gone into it.
So he gave that talk on ranges, and I was transfixed by that talk.
Right.
So I think perhaps a year before, or I'm not saying this to claim that I'm particularly clever, but the year before, I think it was the year before, I'd done a talk on iterators and the way that they're implemented, or what they look like in lots of different languages. And the Python throws an exception to end the iteration, and that's just weird, right?
It is weird.
Anyway. And then next year, there's Andre with his ranges talk, and I sat there going, "Yeah, this is great." And I remember Steve Love was in that talk as well. He was like, "Yeah, this is great, this is brilliant." And then we waited for Andre to do this work, and he didn't do that work. Right. He went off and did it in D instead. Right. So D has really quite a powerful range library.
Well,
which
just for the viewer, like a range is essentially like a beginning and an end iterator, right? Like it's a thing you can move.
It's a bounded iterator, yes, but it's all kind of in one package.
Yeah. Well, and that's some of its power is that it's It turns out like pointers are not the best abstraction.
No, and so also the point about a range is that a range is that they're composable. So you bring, or they're more easily composable. So you bring an element of kind of functional programming into this. Right. And D's range is very, very good and very powerful, and they do compose very well. But also because D is targeting this systems programming space, there's no allocation. And there's no storage in the range, which can mean, for example, that depending on how you construct your range, you might get reevaluation. So you read something and then you do something else and you read it again, and you might reevaluate the whole pipeline.
Okay.
If the source you can, let's say you're reading from it, you're scanning an array or something. Not so. Where I work, we have a scripting language written in D.
Lucky you.
That had has a ranges library, and so that language is more akin to a Python or a Java script or something like that, right? And it's a very functional style and makes it very easy to put together range pipelines, which, if you weren't careful, would exhibit sort of exponential memory use and things, because they were reevaluating bits as you went through. And some of the work I did was then to basically, on top of the D library, was to put in the kind of buffering, so that you stored the intermediate results as you went through.
Okay, so you're sort of reifying things,
yes,
or memorizing,
and recording things like, so obviously some ranges know how long they are and some of them don't, and composing those in sensible ways. And that's my one little bit of D programming.
Nice.
But yes, off the back of that, I get to go to the D conference, and I'm off again in a couple of weeks.
I've already told the story of how I won a D book, so I won't tell that again.
Was it Andre's D book?
I think so.
Because that'll be out of date now, because they changed it all. They changed a lot of it.
Don't worry, I didn't read it. But it is very... Oh, I tell you what, it's propping up my monitor.
Oh.
It's not Andre's. It's by Ali Sireli. That's good. That's a good book.
Yeah,
I mean, it seemed good, but it seemed massive. And
seems a little thin for holding up a monitor. I've got fonts and encodings, which is that big, and a hardback copy of Stevens underneath it to really give it.
Well, I've got programming in D. I've got expert Python programming, the worst. One of the worst programming books I've read.
Okay.
WebAssembly, the definitive guide, which is quite...
I'm assuming it's not the definitive guide.
The thing is, it's quite a good book, and it is very much not a definitive guide. It's like a gentle introduction. But it's quite good. It's quite good. And then I've got Understanding Cryptography.
Well, that's clearly a lie. No one understands cryptography.
I did not. My eyes passed over most of that book, and I do not understand cryptography. We have diverted. Okay, so we have terribly. We're writing a thing called a lookback buffer.
But for the programming language nerds, I think there's the way D does mix-ins is really quite interesting.
Right.
So if that's your jam, have a look at that.
Right.
Right.
I was briefly really excited about it. I just can't get excited about something with a garbage collector.
It's optional.
Anyway. So. We're going to have a look back buffer. We're going to name this test in a minute. So we're going to make one, and it's going to be based on some kind of other stream. So let's just call this writer. Right. So we're going to have some kind of writer, which is it's going to be anything you can write. So like a vec of U8 will do.
Yeah.
And we are going to write to it. So I guess we're going to use the write macro maybe. Right, we're going to write to the buffer some things. And then we're going to verify that they did get written into the writer, I guess.
Mm-hmm.
I mean, this is going to be we're going to write bytes.
Mm-hmm.
I think. So I mean, maybe that's our first test. Just verify that it passes through.
Yes.
Bytes written to bytes written
under
pass through.
Yeah, that's fine.
To pass through, fine. So, given a writer, given we wrap a writer, when we write, then the bytes end up in the initial writer or something, I don't know. Underlying. Okay. This should be, I think we need to do this or something. Maybe I shouldn't be using the write buffer. I mean the write macro. Maybe I should, but it shouldn't be byting it. Anyway, let's not worry about that yet. We're not there yet. All right, so what we've decided is that we need a constructor. Do you agree with this?
Yeah, yes.
So we'll have a constructor that returns a self. Takes in... It's going
to be a dyn mute thingamydoodah, isn't it?
We need to take ownership of it.
No, we don't.
You think?
Right. I think I'm absolutely sure of it.
Okay.
I think it's a mute dyn write.
Okay.
Reference.
We've got to have lifetimes.
Yeah, but it's an easy lifetime.
Yeah, they're all easy. So what are we calling this? Underlying? That's awful.
We just call it out.
Yep, that's better. I like it. All right, so we're going to hold on to out. Do you think we're going to hold on to other stuff or just out? In which case, maybe structs. Like a struct like this.
We're just going to start with out.
And okay, so we need a lifetime on. Look back.
Yeah, it's just going to be a dash A, isn't it? That's it. It's fine.
Right, we need. Is it right? Am I right that it's right? Right.
Yeah, you are right that it's right. It's
right.
Std.io right. No, is it Std.io right?
I think
Can't
so.
remember.
Well, there's two. There's std format right and std.io right, but
it's IO right.
Yeah. And I'm failing to write Rust syntax or something because it's stressed out. What have I done wrong?
Word. I don't know.
I Just, if in doubt, restart your LSP. No, that didn't work. Oh, it should be mute in. Is that
right? Yeah, that's it, yeah.
Okay, that Rust has famously good error messages, but not in that case. All right, so
this is West Dine, is it? East Dine. East Dine. There we are, okay.
Right, so meter needs to be mute, and for the record, buff needs to be mute too. Okay. So, all right, we need to provide the lifetime here. We can do that part. Now, surely it's going to say, hang on, I don't know how to write to a buff. Yeah, so we need to impl write for lookback buffer for this test to pass. Okie doke. And apparently we need to impl flush as well. Well, implementing flush should be easy, right? Because that should be self.out.flush.
Because we just pass it down.
I tell you what, implementing write is going to be easy too. Done. I reckon we can write a tick underscore here.
Oh, because we don't need to use it.
Yeah, I think so. Okay, what's it moaning about? Oh, we need to bring in...
Is that because we've used the right macro?
Yeah.
So if we just write to it, then we'll be all right.
All right, and it produces a result, which we need to do something with, so let's unwrap. Now, it's warning us about unused stuff, which I think we can ignore, because it's used in tests only. All right, I think we have a test, and I think, unfortunately, I think it's going to pass. Okay, let's make it fail, because that makes me scared. Okay, it failed. No,
Very good.
It's a really horrible error message. So let me just make it there. Something like this.
Oh, gotcha.
Okay. Oh, I need to make it fail to see the error. All right. So now our test failed.
Lovely.
We can see. So now it passes. We have made a wrapper for a writer. So next test.
We have. That does no.
Refactor.
What do we no? What are we going to refactor here, Andy?
I don't know.
What are we doing now?
We've gone from red to green. Now next is refactor.
And now, red, green, refactor, commit. Submit thing say red, green, commit.
Well,
to commit. Right.
What did we change? Oh, I got rid of some white space. And then the rest of it is all this. Thanks, Dad.
It's all right.
Draft a look back buffer.
Okay. That's interesting you say draft, because I often say things like sketch or skeleton.
Mm-hmm. Skeleton's probably better.
Draft is interesting, but that's nice. Okay.
What's next?
Okay.
I mean, is it just I can look back?
I think yes. Yes. So I think we need to be able to. Okay. We're going to make a little choice here. We know that for the purposes of deflate, this will always be a 32K buffer. Mm-hmm. But for the purposes of testing, do we want to make the size configurable? Let's come back to that one. Yeah, I think for this, we want to be able to ask it its length or something like that. That's the first step into actually buffering.
How far can I look back?
How far can you look back?
Makes sense. So I guess maybe we could assert that it's 0 at the beginning.
Mm-hmm.
Given a look back buffer with nothing in it. I mean, do we want to call this size?
What would you normally call it? What's the Rust normally call this? Size? Is it size or is it length?
It's len if it's... I guess len kind of expresses it. Like I'm thinking of it as going backwards, so calling it len is a bit weird, but...
It's fine. No. I think length is fine because it's still filling this way. It's just once we hit that, it's just going to do this. But so it's still...
Given a buffer with nothing in it, then it has 0 length. And when we write something into it, then its length increases.
Mm-hmm.
So this should be buff.then. Will now be 5,
11.
Do we want to say, like, it also hits a maximum? That's probably a separate test.
That's the next thing, isn't it?
All right, so, oops. Why are you not offering me to make me a method for me? Why do I have to type things?
You'll grant there's a certain irony here, Andy.
We don't talk about the distance that happens in rounders. We simply write code. All right, well, let's return 0. And... No, not that. And run our tests. There we go. All right, they failed because 0 is not 11. All right,
fair.
So how are we going to implement len? I mean, we don't want to do it in a really cheaty way that's not actually moving in the right direction.
No, we need a buffer in the buffer that we're going to write it into.
Which is probably a vec of U8. Right?
Yes.
Well, maybe not a vec, maybe something else of U8. But we haven't.
Well, is there a kind of a built-in like sort of memory buffer, or do we have to do a vec and put something around it?
I think there might be some kind of circular buffer. We might need to use a library.
Yeah, I think this is simple enough that we can smash through it. Right?
I think we should implement it ourselves.
Yeah. Why not?
Why not?
Come on, Andy. This is like real computer science, almost.
All right. You've sold me. You've sold me on that. So let's have a vec of U8 then. That seems to be the natural. I think it's a vec deck. Or is it just a deck that I was thinking of? And I think such a thing exists. Is it called vec deck?
Well, there's a buff reader. Is there a buff writer?
Yeah, but that's just a buffer, right? That's not a circular. So this is a vec deck.
Oh, I see.
Is a ring buffer.
Okay. Go on.
So,
this is built in.
yes.
Oh, hang on. What am I? Sorry, I'm looking at the wrong thing. Oh. Okay. Yeah.
Collections vector. So it's a ring buffer. You can push back, push front, etc. Let's look up vector.
I don't think it matters what we use at the moment.
That's true. We may be getting ahead of ourselves. Let's make it a vec then. Let's not over-engineer it. So, it's going to be empty when we start off. And I think len is going to return the length of the buffer.
Mm-hmm.
So the only question is, how does it ever become non-empty?
Okay.
So I think it might be just that everything we get given, we push onto... No, just extend, please. Is that a thing, extend?
Extend from within sounds horrific.
We don't want to do that. Okay, so I think we everything that comes into write, we write it into the buffer and then we write it out.
Okay.
So maybe our tests will pass. Our tests pass.
Blimey.
Just like that.
Okay, that was cool.
Yes. What's next?
Are you going to commit that? Yeah.
Include a buffer in loopback buffer. All right, so now we need something that says this doesn't just go on forever.
Hmm.
And I agree with you. We should be able to tell this loopback buffer what size it should be, just to make tests not be missed.
Yes. So, are we going to do that in construction time? Are we going to? Is that going to, or is that going to be? Are we going to do it afterwards and just set the max size?
I think construction's the right time, don't you?
Yes. Yes, I do.
And buffer size is limited. So, given a loopback buffer whose size is limited to 16, say, when we write more than 16 bytes to it, then its length is 16. Right?
Yes.
Is that?
Yes.
We know this is kind of weird because we're going to implement more than we technically need to for this.
Well, are we? But yes, this is separate from checking what the contents of that is.
Yes, exactly.
And we're going to need a separate constructor, aren't we? Like a with max size or something like that.
Yeah, well, I was wondering whether we always specify the size. What do you think?
Okay. Yes, why not? Because then you can, yeah.
Let's just have some other random sizes just for...
The entirely random 1024. Yeah, those random numbers are just popping off there.
I mean, I can't help using simply random sizes. Okay, so I guess are we gonna hold for now? Are we gonna hold size in?
We need to do it now, don't we?
In here, like so. Now we could cheat.
Okay, so we could cheat by just truncating things at the maximum size, or we could start to do it properly. But I am not fussed as to which you choose here, and I may have to pop out with the dogs for 10 minutes because they're all starting to get a bit agitated.
No problem.
So how about I leave you to that, and I'll be back. I'll be back in about 10 minutes.
All right. Well, I'll do a little bit, and then if I feel like I'm rushing ahead, I'll just wait for you to come back.
Okie doke.
And I will cut that out of the video, viewers, so don't worry.
No. Look. There's one of them.
Have fun, dogs.
Sorry, back to him.
See you in a bit. All right, so the thing is, I can make this test pass by just returning the minimum of this and size. Now, that would be really awful, but it would make our test pass, I believe. Yeah, so that kind of feels to me like that means our test is not adequate, because this is a real cheat. We're basically letting the buffer grow as big as we want, and then just misreporting the size. I mean, you could get some way with like just allowing the buffer to get bigger and bigger and bigger, but only allowing you to access some, like the last 32k of it. So in theory, you could say that this was some sort of getting close to some kind of legitimate implementation. But I think what I should do is, why don't I just knock up a couple more tests, and then Jez can help me implement them. So can look back. I guess one thing we could do is we'll do a test that just says something like memory size is bounded. Yeah, I like this idea. Why don't we just ram a huge amount of data into one of these buffers? And we'll have to use a writer that doesn't store that data either, because otherwise we're going to run out of memory because of the writer. So we're going to say, we're going to make something called dev null, which I think we can just make like that, and then we'll make and that's going to, so that we'll talk about this. Then we're going to place our lookback buffer on top of dev null. Dev null is a reference to the Unix file-like thing called /dev/null, which is basically you can pipe bytes into it and they go nowhere, they just disappear. So we're doing the same thing. We're going to make a writer that just ignores everything you send to it, and we're going to set the size to something fairly small. So given we throw away all our bytes and have a small size, when we pipe in an unreasonable amount of data, then we don't crash or slow down a lot. Now, watching this test fail may have implications for the health of my computer or something. So it would be nice if we could somehow measure the memory usage without actually crashing the computer. Especially, I don't want to destroy the stream. I think it's unlikely it would destroy the stream. I think it would probably. What I can do is I can just run a unit test, like not pipe in a hugely unreasonable amount of data, just pipe in quite a lot of data, and then like watch top while we're running the unit test, and hopefully see that it gets big. Let's try something like that. So Well, that's the nicest way to, for some range of, so like a large number of, so let us write 1024 times 1024, again with these random numbers. Well, let's do, can you do to the power of? So let's say 2 to the power of 32. So 2 to the power of 32 numbers, let's just write something into buff. What is this doing? That writes some bytes. So what if we just wrote, can we just write maybe we should use the write macro, or what's write all? Write all is probably what we want. Attempts to write an entire buffer. So we're just going to give it a vec of U8s. So let's make a buffer of the stuff we're going to write many times. Let staff equal a vector of U8. So let's make it a string. Make it from a string rather. As bytes. So let us write hello. Let's write Andy is cool. 2 to the power of 32 times. Let's make sure these are U64s. Or we could have U size. Maybe U size is better. To the power of. Oh, apparently it has to be U32 in here. Or maybe we could just write that then. Yeah. So we're going to write like so. And this shouldn't be buff, this should be stuff. So let's, I've been a little incoherent, but basically make a vec, this is a vec of U8, or rather a slice of U8, which has the bytes for Andy is cool in, and then 2 to the 32 times, that's so many times. Let's do 2 to the 8 times to check this works. Then we write that stuff into our look back buffer. Now it gets the pass through gets thrown away, gets put into dev null, which we're going to write, which is going to throw it away. Whoops. But if look back buffer makes the mistake of caching all these bytes, then it's going to crash. So there's nothing to write here for assertions. It's just like we didn't crash. So let's make our dev null. Null, if I can type null, and we're going to impl write for dev null, and it's going to do absolutely nothing. And it needs to return okay buff.len, I guess, for that, and here it will return okay nothing. Let's have a comment for dev null. Throws a write that throws away what you write. Wonder if there's one of them in the standard library. That'd be useful, I guess. Okay. Now we had another test, which I think we can just to do for now. Or maybe in fact let's ignore it. Like so. It looks like Jez is returning already, and we haven't done much. Okay, so buffer size is limited past because we only gave it a small thing. What if we give it a huge thing? So 2 to the power of 8 was fine. What about 2 to the power of 16? That's a lot bigger. And it ran in almost no time at all. double the size. Did I save that? No. Double the size. Fine. Let's double it a few more times. I don't want to go mad. Did that take a tiny bit longer to run? That took a tiny bit longer to run. You're back, Jez. I thought I was going to run out and have to just sit in silence for you to come, but I was waffling on.
Everybody feels much better.
Okay, the dogs are okay.
They are.
Excellent. Excellent. So let me fill you in on the shenanigans we've been doing in the meantime. So I decided I could make our tests pass with a really horrible, trivial implementation. Let me show you that. I just lied about the length of buffer by giving. I actually kind of hate this. I would rather use usize : min and give it 2 arguments. I kind of hate doing .min. I find it really hard to understand.
That feels more natural.
Okay, so that's what I did, and our test passed. So I became unsatisfied with our tests, and I started writing this test.
Okay.
So I make a writer that throws away bytes, I make a lookback buffer that wraps it, and then I write a lot of things into it, and I don't want to crash.
Oh, okay, lovely.
Now, I wish there was a better way than, especially as I might kill the stream, just making it crash. Let me double it 2 more times. And now we see a noticeable pause when we run our unit test. Let's double it another couple. Another 1 anyway. All right, it's a bit slow. But that doesn't mean, like, it might well be that slow. Even if it was throwing away, it wouldn't be that slow if it was throwing away all the bytes probably, but it's possible.
Okay.
So
why have we got an ignored test?
Oh, yeah, sorry. Yeah, I started writing another test and I've ignored it. So.
Okay.
So I don't know where I'm going with this. Like, I could run top while the unit test is running and verify that it's using a lot of memory.
Mm-hmm.
And then I could fix it and see that that's not happening anymore.
Show me the thing again. Oh, we're doing it in a loop. Okay, that's fine. That's fine. Okay. So are you just going to carry on increasing that number until it does crash?
Well, I don't want to, because I don't want to cause, like, the recording to go wrong or something like that.
So,
but I could.
Why don't we look at write all is provided by the trait? Is it?
Yeah.
Okay. So, why don't we? Why don't we do write properly then?
Well, you mean? What do you mean? Like implement, like actually implement our code correctly, or are you still talking about this test?
Yes.
Implement our code correctly.
Yes.
Because we haven't got a test that's failing yet, so we can't write our code properly yet.
Okay. Why don't we? Is there the equivalent of a vector in C++ standard library has a capacity and a length?
Yes.
And the capacity is how much you can fit in it, and the length is how much you are actually using.
Yes.
Is there a sort of a Rust vernacular?
Yeah,
for that kind of thing?
That's exactly the words that Rust uses for those things.
Okay. So if we also check our capacity and return the real length of the internal buffer through that, then we can write a test which will verify that the capacity does not exceed the defined length.
Okay, so yeah, basically make our internals a little bit more observable so that we can make assertions about them.
Yes.
That sounds good. So then we could have an assertion like this. Buff.capacity. And then we just have a contract that you don't lie with your capacity.
That would be fine, yeah.
So the capacity should be less than, I don't know. I mean,
well, it should be less than or equal to the length. And both of them, in this case, should equal 16 because that's the number that we poked in at the top.
All right, so length, I mean, we're not checking length here because we checked that in a different test.
Mm.
So here it would be then our capacity did not exceed the specified size. And then we just have a contract on capacity, a gentle person's agreement that you don't lie in your capacity function. Capacity. So that'll be buffer.capacity. It's that easy. Okay, so we've written a lot of bytes. I mean, maybe this test is now massively over-engineered, but we've written loads and loads of bytes, and our capacity never went over 16. Happy? Fine. It takes a long time, and then it fails. Now, we'll see whether it actually takes a long time once we've done a good implementation. If so, I'll make it smaller. So, how are we going to do a good implementation of this? I can't hear you anymore, Jez. Is it you?
I turned the microphone off for a moment. Yeah, if we make that an assert eq at the bottom there, then we can see the actual size of the capacity.
Right. That'd be nice, wouldn't it? That would be fun. I mean, it's going to be 2 to the 25 times. I mean, it's quite a bit bigger than 16.
Quite large. Okay.
Okay. Bytes, kilobytes. It's only 402 megabytes. It's all that time is spent reallocating our vec.
Yes.
So it's going to be fast once we've done this right.
Faster. There's still quite a lot to throw away.
Okay, so we're going to implement it. Let's do it.
Yes.
So I guess we want our len to return the actual length of the buffer, right?
Yes. So we should allocate our buffer. Mm-hmm. We should allocate that up top.
Yeah.
With our size. Yeah. Now, does that for a vec? That is there a fixed like an array type rather than a growable type?
I mean, we can use an array.
I appreciate that we can use a vec in a kind of a fixed size way, but I just wondered if there was an array type which won't grow.
I think you spell that something like that. Is that a thing?
That is a mouthful.
I'm not even sure.
But can we? Oh, I see. Okay. I don't know. Let's wind it back to vec because it feels like now we're going to have to do something funny in the struct declaration because we don't know the size, which is why you've got to box it, right?
Exactly. Because size. If size was known at compile time, we'd be fine. We could just use an actual array.
Yeah.
Yeah. I think it might be. No, I think it would be that. And we don't like that. I think we prefer.
No, just okay.
We know that vecs are extremely efficient if you never resize them, so we don't have to worry too much.
Okay, so we don't. And right, and our capacity. So with capacity.
So now this is an empty vec, but the memory's been allocated in its backing store.
Yes. So we now need to do our kind of classic pointer chasing thing, right? Index chasing.
Because we're going to write a circular buffer.
Because we're going to write it, and as we pop off there, we're going to whip round to this end, and when we hit this, we're going to, yeah.
So we probably don't need to hold on to size anymore, because the vec, we're never going to change the capacity of vec, so we could always ask its capacity.
Is the capacity of a vec exact? So because I'm just thinking about in C++, the capacity, if you ask for a particular capacity, you'll get that, but it might be bigger.
Yeah, that's an extremely good point, look, at least.
So maybe we do need to hang on to the size.
I think
just to be on the safe side.
I also think that means we can't actually do this assert eq.
No. We can do that assert because that's our capacity, but we need to change the implementation of capacity to be length.
Well, really? But then... Fine.
Or something else, right?
No. I tell you what. I want to return capacity here because I want to know actually how many bytes we allocated.
We're going to get, okay.
So I don't want to assert that it's exactly 16. I want to assert that it is less than some reasonable number.
Yeah, so we want to, but we need another member, don't we?
Mm-hmm. Yeah. Right, sorry, just making sure our test states something that I can back up.
Okay.
Right, yeah, so we're going to want something for like the start, I guess?
So yes. And we don't need to keep the end because we can calculate that from the size. So it's actually just the write index. Is it? Oh, no. Because until we filled it, We'll find this out in a minute, won't we?
Do we need more tests? It feels a little bit like we're implementing some kind of ring buffer that needs its own tests. Or...
Well, that's what we're doing, yes.
Should we do that?
The fact that no, this is the ring buffer, though, isn't it?
Yeah, but
this is the ring buffer.
It's also like a writer wrapper, but
yeah, but that's like a one-line thing. That's nothing, right?
Fine. Okay. So, how are we going to test this in a way that is good?
Okay, so
I mean, I guess until we filled it, the start index is going to be at 0.
Yes.
I think
and the end.
I think we just want some tests.
Just want start.
Yeah, I think we only need to hold start. But like in terms of tests, I think we just want to keep adding bytes until it overflows, and then check.
So no. But we've got stuff we can change. We've got some examples here already, right? So let's go back to our write.
Right.
Our write implementation. So that line there, extend, has got to go. The write at the bottom is fine. So half of me wants to say we iterate across our buff and write a byte at a time.
So there are. But
otherwise, we can do sensible things, right? Like, does it fit in the space we've already got?
There is a std.io copy that will do something, maybe.
Yeah. So we've got two cases, right? One is the incoming buffer fits exactly into our vector, in which case we insert it into the buffer or copy it into the buffer from our start index. Or it won't fit into the space available in our buffer, our vector, in which case we write as much as we can, reset start index, and then splot that over the top instead.
So the second case is easy. So why don't we do the second case first?
Is that not the first? If the incoming buffer sits inside our vector, I was being very careful to say vector so I could separate the two. Copy it into the vector from our start index. So that's the easy case because that's the first case when it fits exactly.
Fits exactly?
Sorry, it fits without any overlap. That's what I mean.
I think
the whole of the buffer fits into the vector. Buffer len is less than our remaining capacity. What's our remaining capacity?
Oh, our remaining capacity.
It is size minus start index. Remaining capacity, lovely. Or distance to end or something like that.
Yeah, okay, hold on. Yes. So that is
size minus start index.
Is it size or self? No, it's size. Yes.
Size.
Self.size minus self.start index.
Yeah.
Okay. Then we just copy it in.
And if it does, then we just splat it into the vector from the start index. I don't know how we say that.
Something like that?
Oh, is it like that?
I mean, probably not.
Its start is a self-start index, but we can, yeah.
Now, something like this can be done, but I think it's unsafe because we can't guarantee that the two slices are the same size. But we happen to know that they are, right? But it's not actually letting me do this, so I might be just lying. Getting closer, we're getting closer. Cannot assign to this expression. It's not saying it's unsafe, it's saying I can't do it.
Do we have to do... Oh.
There's all kinds of stuff in here.
Oh my God.
These vectors are like overpowered with stuff you can do as mute slice.
Oh, that's mute slice is
that's the same.
It's going to do it, isn't it?
It's the same as saying ampersand mute. It's saying here equivalent to what I just tried.
Oh, I see. Right. Okay.
Well, maybe you can call a method on an unimmutable slice to like replace it. I feel like there must be an unsafe thing you can do.
Copy from slice.
on a vec or
on the vec. So you've got the slice of the vec, and so you don't need any of the unmute business. No. Go unwind all that.
Like this.
Yeah, but so we got self.buffer brackets start ... end.
Right.
Copy from slice buff.
What? Just like that?
Just like that, according to this web page I found here.
Yeah,
because that's what the web page says.
Self is a slice.
Just to reassure people, this is not from Stack Overflow. This is from users.rustlang.org.
Is that better? Sounds worse.
So it must be true.
The length of source must be the same as self. Right, so yeah, self is a slice. We're calling copy from slice. What happens if it's not the same length? Panic. It'll panic if the slices are different lengths. Good, okay, we want that level of protection. We believe they are the same. In fact, we guarantee that they're the same.
We guarantee it.
So we're okay, so we don't need to do... Like, it's so obvious, I'm not even going to add a comment. Fine.
So, if it is more than, then we are going to... Oh my God, we've got 3K. So, okay, yeah. We can deal with...
What if it's massive?
We can eliminate that in a minute. We can eliminate that at the outset. That's fine. So, otherwise, if it won't fit into the remaining space, we copy as much as we can. Then we reset the start index and copy the remainder.
We actually need to update self.start index here, don't we?
Oh, yes, we do, yeah.
So here we're going to do... something. Right, is it something like this?
It's going to be buff square brackets 0 ... distance to end, right? Well, this is okay.
Oh, what? Don't do that. Like so. Now, what are you moaning about here? Oh, let's just put start here.
Yeah.
Okay.
That's nice. Then we reset start. Self-start index equals 0. Now, okay, let's assume, and we can make this safe in a moment, that the rest of it will fit. Can you take a 0 length slice?
Hang on. Oh, that should...
We'll find out in a minute. Doesn't matter. Come on.
Yeah, that's a really good question. Let's just...
I think it doesn't matter. We can find out in a moment, because I think again it's
we're going to write a test for this edge case. That's what we're going to do.
Yes. So then remaining buff, and then we plonk that in exactly the same way that we just did above.
Right. It's kind of...
It's that. We can factor that out in a moment, but yeah, it's this again.
So I actually want to put start back in. I'm really uncomfortable with moving it out.
Okay, it's fine.
And then start needs to be like, I've got to fix all this in a minute. All right, so
yeah, it's fine. Right, but this doesn't cover the case when the incoming buffer is massive.
No, and it also...
Right.
There may be other edge cases. So can we write tests for these cases?
Yes, we can. Yes, we can. In fact, we have some already, don't we?
I mean, we have one test where we're only checking length.
No. Yeah, well, this is bigger.
Yes.
This is going to fail, I think. Well, we should check the capacity in that test as well. 4 failed. Maths, absolutely. Oh, okay, there we are. Look. What is going on there?
We've got so many bugs. Source slice length 16 does not match destination slice length 0. Doesn't sound good.
Okay, line 44 and line 48 are problematic. Let's have a look at them.
So destination, so buff.len must be 0. That's why we're getting a 0 length slice, and then we're trying to copy a 0 length slice into it. That should be okay. No, that can't be that. What have we done wrong?
I don't know, Andy. You're the Rust expert.
I should put that there for a second. Yeah, it's just the programming bit that I struggle with. Okay, so let us just think about these cases. Like, we need tests that check these things nicely, right? So 44 failed means that it is getting into this section and it's still going wrong. So that'll be, I'm guessing, it'll be in our test, this test. We're trying to write hello world into something of size 1024. So it's got plenty of room. And it is crashing. So we can reason this out. All right, so we've got a buffer of size 11. So the distance to the end will be self.size minus start index. Start index is 0. Self.size is 1024. So distance to end is 1024. Buffer length is 11. So we do end up in this if. Start will be 0. End will be 11. So then we take a slice from 0 to 11. And we do copy from slice and copy in buff, which is of size 11. And we crash. And let us just run this single test. There's something wrong. I guess it can ask how far we can look back. Yeah. So range end index 11, out of range for slice of length 0. Ah, okay. Our vec is not long enough. That's what it's saying. So we're trying to write into a vec of size 0. Buffer has something.
So with capacity doesn't fit. Okay, so we need to initialize our buffer then, do we? No. Do we want to do it here, or do we want to?
Well, yeah, we could always just say it always has a fixed size and never changes.
Yes. So why don't we just then 0 initialize the whole thing?
Okay, let's do it. Which is not that easy. I think it's going to be 2 steps to do that.
Mm-hmm.
We could make it from raw parts, but that would be a bit... So let's do it. I think there's an extend. We can extend with repeat. Is this really the best way of doing it? This can't be the best way of doing it. I don't even know how repeat works. Endlessly repeats. Okay, so I think this works, but I hate it. I think actually we can do better. Can we? I feel like there's a set size, but I can't actually find it. Oh, I tell you what we can. No, I was going to say we could make an array of 2 vector.
Right, but which version of Rust are we using here, Andy?
We can use whichever one you like.
I'm using 1.5.0 or above. We are. There's a fill.
Yeah, but it already needs to have a size. Oh, look, there's a macro. There's a macro for this. It's okay.
It's always there.
It's just the same as what you would do for an array. It's just that.
Does that fill it with anything then, or does that just set the size?
It fills it with zeros. That's what the zeros for.
Oh, really?
It just needs to be. It needs to be.
Oh, okay.
Hold on. What?
Is it it's a colon.
Oh, yes.
It's colon size. Otherwise, it's just literals, isn't it?
Yeah. Yep.
Sorry, yes.
Yep. All right, and then we can actually put this in line again. All right, it was easier than I was making it. Okay, apologies to everyone shouting at the screen. Yeah, so yeah, it's really nice that the vec exclamation mark macro looks exactly like how you would make
the literal macro.
How you'd make an array if size was known at compile time. All right, so now
something initializer lists, but anyway, carry on. Go on.
No, there's no initializer list pane. All right, so now this test fails because we asked for the size.
Because that's a real failure.
Yes.
Of something.
Well, no, it's we ask it for the size, and our vec size is now fixed at the size we asked for. Sorry, we asked for the len, I mean. But we've changed our implementation so the buffer is always 1024.
Okay. So, do we now need then? So, right. So len and hopefully capacity are just going to return the same things. That's fair enough.
So I'm not sure it's right that we're initializing it to this size.
But we want, yes, I think we do. Sorry, can we just have a look at the test again? Let's see which ones. It is just that one that's failing, is it?
Yeah. I'm only running this one at the moment.
Oh, okay. What about the others?
The slow one is slow. So only this one is failing.
I think, right. Okay, so, take us back to the test again. So, this is interesting, isn't it? Because how far can we look back? Okay, so we start, there's nothing in it, we can't look back at all.
Yes.
We write something that will half fill it.
Yes.
In this case, so then we can look back, or that fills it a bit, then we can look back that far.
Yes.
And that's true until we flop over the end, in which case, then we can always look back the maximum amount.
Yes.
Our start index is not enough for that.
No, If we didn't initialize the vector to 1024,
but then I think the bookkeeping becomes, because then we have two modes to fill it, right? One is we extend it until it hits the end, and then we start copying in.
Yeah, but the alternative is that we do, like, basically it's tracking len for us. Otherwise, we have to track len, right?
But we have to do that anyway.
Do we? Not if vec is, not if the internal buffer length, it just is the length.
Okay, so it's not like a sort of a circular buffer or ring buffer or something where we're putting things in and then we're taking things off again. So these two are kind of chasing each other, right? We're only ever interested in how far we can look back.
Yeah.
And the reason I'm saying that we should loop off the end and come back at the beginning is because that's a cheaper operation than copying the block back. But maybe we just copy the block back. Maybe we just shift the vector, because we're only dealing with 32K. We just shift the vector back and then write some more. And then the len will do it for us.
No, I think the len will do it for us anyway. The size of the vector is always the number of bytes you're allowed to look back in my setup. It's either a partially filled vector, in which case there's nothing difficult, or it's a full vector.
Okay. So how do we rework right to accommodate that then?
Well, now you're asking. So let us think this through slightly. So that would mean that this was a vec new.
Mm-hmm.
And then when we write, basically, when we're going to write into buffer, we need to make sure that buffer is at least as big as the end index, right? So we need to do something that, like, what does fill do this? Like, what does fill do?
Oh, I see.
No, we want to something that, like, adds to buffer the right number of things. Fill with? No. So we can extend it by, like, we can do my trick that I did before. We can extend it by the amount of extra that we need, which is basically its current length minus what is it? It's end minus its current length. Right? It should be, I think it's a repeat. Make sure the buffer is at least end long.
Oh, right. So if it is end long, then this will do nothing.
Yeah, which feels horrible that we're doing all that for nothing. Probably okay. And now we've got space to copy from start to end, because it's as big as it.
Okay.
And then this here, it needs to be as big as size, I guess. So it's going to be something like size minus len.
Why does it need extending in this case? Because we might not have filled it all already. Okay, yes, go on.
Is exactly size long. We should have a comment here saying data doesn't fit. The new data is going to overflow our buffer. It should be self.size. Right. So, do you hate that?
I don't yet. Go on.
Right. Now we know.
Okay.
Oh, we don't actually. So now huge buffers are going to crash, right?
Yeah. Let's run this and see what happens then.
Well, that test passed, and our slow test is slow.
Okay. That's interesting. What's our memory size? Can I ask how far back we can? Can we look at how far back we can look test again?
can ask how far we can look back.
Okay, can we write hello world to it again and check that we max out it? Can we wind our buffer size back to 16?
That's this
in
one.
That's in that same test.
But isn't this test already testing that?
No, because we're asking. So well, maybe we are.
I mean, this all does it in one step. Maybe it would be nice to see it in multiple steps. But
I would be. See, I don't know what's going on in that one. But there are other tests we can do for that. Okay, that's fine. That's fine. So yeah, if we write this again, then we should max out at 16, right?
Yeah. Oh, and when we write,
as long as we make the size 16 at the top there.
Just for my enjoyment, let's just make it a different number because I hate having
Okay, all right. You know, I thought we'd be a sharp 45 minutes in and out this evening.
Then its length is limited to the original size. Right, so shall I run that?
Yeah.
I'm sorry, obviously feel free to stop whenever you want to. It's still happy. It worked.
That's good. Okay. That's fine. Okay. What's buffer size limited? Okay, down we come. So that is writing more than the buffer.
Yeah, so the capacity is going to overflow here.
But I think we're writing the wrong thing.
Oh, yeah, you're probably right. Which is why can look back or something like that is
right. So, which is why we need to start looking back into the buffer to check that the right stuff has been written, which I don't think it has.
Yeah, I agree.
I think we're truncating from the wrong place. Anyway, right. Yeah. So index and offset are what we're looking for here, I think. So we're and we'll worry about bounds checking and things later on. So let's fill it exactly. Oh, nice.
You want to fit it exactly?
No, okay. If we fill it exactly, or we don't, if we underfill it, then that's an easier test to write, and we can feel happier that we've got that our look back is returning something sensible, right? And then we get the more complicated case when the start index is no longer at the start.
So let's write 10 bytes into a 16-byte buffer, and then look back 5.
Let's look back 5 and ask for 5.
Ask for 5.
Or 3, yeah.
Simple to test.
3, oh, that's fine. Then we get
asking for 5.
5, 6, 7, 8, 9.
And now let's look back and ask for 3 just for, because now it's easy to see what the 3 should be. So then we can look back for something. I don't know what. Then we can look back into the buffer, something like that. All right. We're going to look back is easy to implement. No, it's not. To make this test pass, look back is easy to implement. Right?
Mm-hmm.
It's going to return a slice of U8. I wonder if that's going to be okay. Start.
So it's
length.
It's offset length, not start. It's offset because you're offsetting from the end.
Oh, right. So that's really weird, isn't it?
Yeah.
If we ask for 0 bytes, we should start from len because that's one off the end, right?
Yes. It's yeah. It's why have you made buffer a function there? What's going on?
Oh, no, because I'm just wrong.
Yeah. And we can come. I'll come back in and fill the bounds checking in later on. In the specific case for the deflate stream, we know that these offsets and lengths are always going to be safe.
Right.
In a more general case, they may not be, but in the specific case for the deflate stream, we know that they'll be correct.
Okay, that's interesting. So then we could just panic if they're wrong.
Well, this is going to panic anyway, right?
Yeah, but
if we try and slice something that's out of bounds.
Yeah, but in a horrible way. All right, so I think that test will pass, right? Well, not if it doesn't compile. All right, we're trying to make... All right, from UTF-8 takes a vec. We want... how do you make a string?
Lossy?
I mean, we could do lossy and it would work, but it's... Now it's not a string anymore, it's a cow. Okay, I guess the point is if the lossiness causes some loss, then there's a bug and we'll see an error. So it's okay. Okay. Has that already passed? I really want to make that test shorter now, it's getting slow. Yeah, can look back with
okay.
Who's passing?
Commit.
You feel like we've cheated. You shouldn't.
Well, we have, but we know we've cheated.
Yeah.
Because we're professionals, Andy.
Yes. Correct.
And this is how real software is written. Believe it or not. I had quite a long meeting at work. Well, not quite a long meeting at work, but we had quite an extended discussion at work, which ended up with us going, we should really find out what it is that they want to do this for. With the answer hopefully being, nobody knows why we need to do this, and then we won't actually have to do it.
That's the perfect answer.
I think we've got one of those kind of sandwich situations where somebody up here has said, oh yeah, it would be really great if we did this. And that's come directly to us, whereas the people in the middle who are actually using our software have got no notion, no idea about that. You know what I mean?
I'm trying to make a string that it's easy to see the length of.
But it's gone wrong.
Right.
Yes.
So now we're going to look back for the last 5.
Which is going to give us C_D_E. But if we stick to Andy's testing dictum, we should change 5 and 5 and 5 and 3 to something else.
Oh, good. Like it.
That's what it's called now. Andy's testing dictum. So now it's _C_D_. Oh, yeah, okay, yeah.
Hang on, we're going back 4. I've changed everything.
That'll be _D. Yeah.
Did I get this one right?
And I think you did get that one right. And this is going to fail.
Yeah, and while we're here, let's just make this test not so obnoxious. Okay. Yes, it fails. So we expected this because we're professionals.
Right. So there are two things going on here.
At least.
One of which... No, are there two things going on here? Yes.
Yeah, there are, because look back is cheating, but also we're not sure that right is actually correct either.
Yeah. So
look back needs to take into account start index.
Yes.
And that means it can't return.
So this is only safe if start index is 0 at the moment.
Yeah, and this we can't return a slice because we're going to have to stick 2 bits together.
Okay, I think longer term we probably want to return an iterator here, but in the meantime I would be content with a vector.
How about a pair of slices that we can then easily iterate over later?
Yeah.
Should we try it?
Because then you can zip them together, right? Is it a zip or is it a concat? Whichever one it is. We just use a built-in iterator, a library iterator that loops over the top. Yeah. And the lifetimes are fine because they're both things that are in our buffer.
Yeah, they both have the same lifetime as self, basically.
Yeah. So that would be fine, wouldn't it? And then that would give us the iterator if that's what we want. Because I'm being a bit naughty and thinking ahead to when we use it.
Yeah.
We're just going to copy from this to the output, which, oh
dear, something bad happened.
Well, here's the thing. Maybe we don't want to have an iterator, because what we don't want to be doing is writing into this while we're reading out of it.
Right, yeah, that sounds bad.
So let's have a pair of slices.
If we have a pair of slices, we still can't write into it while we're holding on while we're using those slices.
Yeah, but that will be fine. That will be fine, because then you've got to kind of copy it or do something else. We'll worry about that later.
Okay, I'm trusting you, and I'm not thinking about that. I'm going to write myself a little function called s, which turns a slice of U8 into a string by doing this thing. Input. That should obviously be a slice.
Let's do 2 slices, so we can do that, and then we can...
I love the way your brain is off. It's so good. So now my test. Oh, you can have an empty slice, because like this is an empty slice, isn't it? So yes, you definitely can have an empty slice. I'm talking rubbish. This is what I should be putting into the test above.
Yes.
But yeah, we'll come back to that. Okay. So this is from 555. And it should be 5, 6, 7, 8, 9. And empty, and then this is 5, 3. And it should be 5, 6, 7. All right, so that test is right. I tell you what, we should really be asserting what happens when you join the 2 slices and not actually asserting what's in the individual slices.
Come back to that.
So now our assertion should be that the 2 slices together add up to this. But I'm not quite sure what we're going to... Hang on, we can work it out. So, how long does it? 16. So we go 10, 11, 12, 13, 14, 15, 16. So C
it's the last byte.
Yes.
And then D underscore D underscore E are our, so that is what we're expecting. And so for the second case, which is 4.2,
yeah, I've broken that somewhere.
we're going to be are we though?
I reckon.
Let's find out. Let's find out.
Let's find out.
This reminds me very much of when I was doing my my software tools in C++ thing, where I was going through software tools in Pascal and rewriting it all. There's a section in the middle where you build what they call a keyword in context index, which is basically an index of all the words in a text corpus, and the kind of where they, and I forget how it works now, where they appear in all the sentences. So if you look up a word, the display that you got was like this word centered in the screen, then with all the sentences it was in aligned to put that word in the center of the screen, right? Does that make sense? So you're having to shuffle around, you're having to offset all the sentences by different lengths, and some of them wrapped. Mm-hmm. And they might wrap at that end, or they might wrap at that end. And I spent an awful lot of time working out how to do that.
Yeah.
And I spent ages on it. And then in the end, I came up with what I felt was really quite an elegant solution. The details which escape me at the moment. But this is starting to feel like that. We've got this bit, and we've got this bit, and it's showing us.
I feel like there might be a few cases.
Okay, so
if end is off the end, then that's one thing. Like if
no,
okay. Like this.
So our case at the moment is correct for when start index is 0.
Yes.
And when start index
is like 16 or something, aren't we?
So again is self.
Start is wrapped round to 4. Has start wrapped round to 4? Have we done that? We haven't done that.
Okay. I might need to get some visual aids. Okay. So we got a buffer of 8. Here we are, right.
Okay.
And I'm trying to get this to, I don't know which way round I am on your screen now. So we're going to start writing from this. We're going to go 1, 2, 3, 4, 5, 6, right? Mm-hmm. And we want to look back 4. So we go 1, 2, 3, 4. Mm-hmm. And then we read forward like 3. Okay?
Yeah.
Lovely. But if we've gone, right, we've written some more and we've written some more, then we start coming back round to this side.
Yeah.
And now, when we wind back, we need to go from there, right? And we go 1, 2, 3, back here. Yeah. My fingers are all the wrong way. Well, polarities are all reversed. Yeah. So, our begin here has to be something like, I'm going to say self start index plus the buffer length minus negative offset. And if that is less than the length, then we're okay. And if it isn't, then we need to get into some funny business. No, that's not right either, is it? Because then we've got to copy the length.
I feel like a diagram is in order. So we've got a buffer of 8, and we've got our start, which is somewhere. Start index is somewhere within the 8s. Let's have that big start. So the cases are if
is there in the Rust standard library like a bounded integer or an integer that
no, but we can
swirls around like a modulo integer.
We can percent it, but I don't think there's one that does that for you. We could write one.
No. I know we could, but then we'd have another 2 hours.
Yeah, Andy would have to be writing unit tests all night just for that.
Did these bloody idiots ever ship anything? Yes, they do.
Yeah, and it doesn't have any bugs on day one. All right, so look, we've got a buffer with a start index. If the distance from start index to the end of the buffer is bigger than or equal to the length we've been asked for. Oh, no, it's not that. It's the negative index. Sorry, yeah. So there's start index, and then there's negative index, which goes back from start index. Right? Negative offset. Negative offset goes backwards from start index. Or rather from the one before start index? No, because start index is like the end. So if...
Hold on. Sorry, go on, keep talking. I don't know, I'm thinking of something different now. Yeah, go on, okay.
So negative index has wrapped...
No, negative index doesn't go backwards from the start index, or does it?
It goes backwards from like one before start index, depending how you think of it.
Ah, yes, because if it's 0, then it just pops around to the length. Like it, go on.
Right, there's 2 cases. Either it fits... We're only being asked for bytes split up between negative index and start index. Oh, no,
yes.
There's more cases. There's more cases.
But, okay, so...
No, there's only 2 cases.
That case, but then you can adjust the offset, and then you get the second case.
There's only 2 cases, aren't there? This has 2 slices. This is 1 slice, essentially.
Yes.
Yeah. Okay. So let's try and write code for these 2 cases. So if it didn't wrap around, that would be... Let's do... If we didn't wrap around, that would be that negative, like the index indicated by negative offset. So I guess we'll call this begin. Right. So begin is start index minus negative offset. Now we are worrying about negative numbers here.
But that's fine. So
no, because these are use sizes, so they're not allowed to ever be negative. So it's not fine.
Okay.
But
right. Okay. So that in that case, if the negative index is greater than the start index, or okay, if negative index is which case is it? So if the negative index is less than the start index, don't make it less than the start index, then we're in our happy case above. We're in our first case.
Right, good. So then we can say let begin equal start index minus negative offset.
Yeah.
and there's only one slice. So the answer is just some kind of slice.
Yep.
Like the interesting slice, followed by a boring slice.
Yes.
Which is from...
Biffa.
from 0 to 0.
Yeah. And so the interesting slice is...
Begin
Start to begin plus offset.
Oh, yeah. Length. So let's just call it end. Plus length. And then we've got like some kind of to do here for check bounds, which you're going to do later.
Yeah.
For bad length blowing bounds.
Yeah, because basically then the length has to be less than the offset.
Get rid of all this rubbish. Okay, so all we have to do now is the hard case.
So, in the hard case, then we've got from start. So in that case, we've wrapped. So we've got
really suited for this job.
The second slice is from the beginning of the buffer to the start index.
Yeah, so begin 2 is 0.
Yeah.
And end 2 is start index.
Start index.
And begin 1 is negative offset minus start index, I think. Or is it length minus that?
Length minus negative offset minus start index.
Size. Self.size, right?
Yes. Yeah, why not? And then the end there is the end of the buffer. So that's just going to be begin ... right? Begin 1 ...
Right, yeah. Now, what if the buffer is not full size? Have I made our life hard by doing that?
Then that we can't support that, because then the offset will be greater than the length anyway, and that would be invalid.
Oh, we wouldn't be in this.
That wouldn't ever happen.
No, but like sometimes self.buffer is short, right? But you're saying
yes.
Oh, but it would be.
But if that's kind of the bounds checking stuff at the top. So if we ask for an offset which is more than we've read, then that's invalid, and we would just explode.
Yep.
Either by so actually, eventually this can become like like I say, something returns an iterator, or something returns a result and a thing, or something. We can toughen that up.
Yep. All right. Let's just...
yeah, that's looking much better. Okay, almost.
Line 46. End was off the end. We asked for up to number 20. Is negative offset, have we given it as a negative number? Something like that?
No.
So let's have a look at the test. So this is, which test? Can look back after overflow. I assume we think it's 6,6.
Mm-hmm.
So we appear to be asking for end to be 20. Is that what it said? Yeah. So we're asking to slice.
Okay, so hang on.
Oh, it's because write's not doing the right
10.
thing.
10. Oh, yeah. But it's because we're not. I suspect if we write this in 2 chunks, I think it might work.
Should we try?
Yes. So write the first 10 and then the next bit.
I don't think we're updating start index ever.
That's better.
Look back buffer 197.
It's wrong, but it's better.
So we thought it should be _C, but it's actually 4, 5, 6, 7, 8, 9.
So it has looked back 6. It's just looked back the wrong thing, right? Which is interesting.
Like, what are we doing? Is write like at all working? Should we print out the contents of our buffer to figure out what's happening?
Yeah, sure.
Let's make our buffer debug and then see what's in it.
Because I think this is our write starting. The write is wrong.
Oh no, we can't derive debug. We need to.
Why not?
Because this, we can't
Oh, okay.
But we can impl debug. I guess. I think you can do that.
Mm-hmm.
No, it likes to format debug or something.
I think. Oh, hang on. Did I do this somewhere? I think I might actually know how to do this.
There's 2 debugs, and I was implementing the wrong one. This is what we should be doing.
Oh, I did display, did I? Which is a different thing.
Yeah. Display is more normal. We could have done that. Do what
display is remarkably similar.
Yeah, we could have done that.
Just does it have to match?
No, we could just not print it.
Cool.
Okay. Oh, that's horrible. Anyway, the start index is 10 and the size is 16. So we did modify start index.
But we haven't wrapped properly. Can we
make buffer look nice?
We've definitely written something interesting to the front there, right? Look. That's an underscore, isn't it?
Right, yeah. I really wish...
So we have written the right thing, and the start index is in the right place.
Is it?
No, it isn't. Yeah.
I think it's start index should be at 4, right?
Okay, let's go. Let's have a look at right.
Yeah, 4 then.
Yeah.
Okay. I wish we had better visibility, but yeah. Okay, so where's right? Here.
No, we haven't done it. We've just... Go on, down you go. Down. Stop. Oh. Ooh. Oh, very good.
But I don't think... Do you think that's relevant? Like, our start index is not...
No.
Just in case. No change.
So...
Oh, hang on. But we shouldn't be moving it along by buff.len. We should be moving it along by the amount we copied. Remaining buff.len.
Remaining buff.
Yeah. Okay. That's the bug.
Yeah, then we need to get rid of that .len.
What .len?
Oh, no, sorry. Excuse me. That's fine. It's my mistake.
Okay, what do we get to? So now start index is 4, which is what we expected.
Good. Yes.
Now we're failing at line 213. This one, it's not underscore D. It's giving us back underscore D underscore E. So it's not using the len properly. It's just going to the end.
Okay. Well, let's have a look at that then.
Oh, it shouldn't be start index.
Start index
Minus something.
minus length. No.
It's this case. So here, in this case, it should be 2. No, it should be... Yeah, it's up to start index is what we thought. But that's because we haven't considered length at all in this example.
No, we haven't.
And neither here either.
So the length
so length will either be...
The length can be up to negative index is wrapped around. So
Thank you.
and then the bit that we need, the extra bit we need is the definitely in that chunk, aren't we? Start index is 4. I think it's 4.
You know what? The end is just the length minus whatever that has already come off the length.
Start.
Right?
Okay. The end minus begin 1 is begin 1, surely.
End 1 minus begin 1 is how much has been chomped up here, and then the end 2 is just from 0 up to how much length is left after you've chomped off those other bits. Now we guarantee that length equals slice 1.
Go on.
Don't shout. I think I'm right. Let's see. Attempt to subtract with overflow. Attempt to subtract with overflow. Okay. I guess I was not right.
Unwind that. Take us back to where we were before, and let's have a little think about
I
it.
still think that's approximately right. Like,
I don't know. If the negative offset is wrapped around, we're always going from that start index, begin 1, to the end. The length of right. And then the remainder is, what have you got here for N2? It is, it's self size minus begin 1. So it's offset minus Sorry, it's length minus whatever's left over.
Yeah, this is what I was going for.
Self size minus begin one. Yeah, okay.
Right?
Yeah, feels like it. That's a different error.
How is that different?
Well, it's got less output now. Or are you just taking the output out? Okay.
No. The test with the output passed. There's only one test failing now, which is the memory size is bounded one is doing an attempt to subtract with overflow.
Okay.
So we could print out some of these things. That's probably enough.
Mm-hmm.
It's going to print a lot, I think, because it's... No, it didn't print anything. So it's before we get to this. So I guess it's the begin one calculation that's causing us to go negative. Negative offset quite large, maybe? Hang on. Where are we? Are we in right? No, we're in look back. Is look back even being called in this test? What is going on? Okay, It's not look back. It's on line 94. Think about it, Andy. So that might be correct, what that code we wrote.
Oh, yeah, because that test started passing. The reason it wasn't printed, okay.
Yeah. So line 98 now. All right, so here we're ending up with a negative from this subtraction. So we're trying to make the buffer at least end long, and that means somehow it's even longer than it should be already, and therefore we're trying to make it negative amounts longer, I think. And that's because...
Well, let's see what that is then. So let's see what start and end are.
Zero and 12. This is in the memory sizes bounded test. Let's just check how big the buffer is. The buffer is supposed to be 16.
And Andy is cool. Is 12 long.
Bytes long, yeah.
So we write 12 bytes.
0 and 12.
And it writes 12 bytes, and we're fine.
And then it does it again.
And then it does it again. So why is start index not?
Because we didn't percent it, maybe?
But it should fit. This is our case where it fits.
Oh, yeah.
So why are we getting start is 0 twice?
Start index should be 12. But now, by the time we got to here, start index is 0. Why? What's happened in the interim? Where does start index get modified? We're not creating a new one or anything like that. Yeah, we set it to 0, but that's in right, but this is in the other branch, which we're not getting into. We are getting into the other branch. And we're messing up the start index somehow. So the first time round, everything
that's interesting. Oh, that's interesting, isn't it?
But the second time round, we're overflowing the buffer, so we should get into the other branch.
Look. We're hitting this because we've wrapped round a few times, and our start index is right back at the beginning. Okay. Up. Code up. So we now want to extend, or we're checking our buffer is at least this long, but it is already. So we want to write 12 bytes to it, but we've already maxed it out to 16. So end minus self buffer len is -4. But you did the thing just below to make sure it's exactly that long.
Exactly size long, yeah. But here we're not making...
I think that's a no-op. I think you can take that out.
Because we will never...
Because it will already have done it. Oh, no, it won't. Because in fact, no, it's not a no-op. Leave it.
Yeah,
because we're going to go 12,
0,
and then the next one, 12, we're going to go, oh, we need to put another 4 in.
Yep. All passes, we're done. I think
commit that.
I think we need to understand this, but yeah, let me.
No, it's fine. It is fine, and I think, right. We can. There's a whole load of it's like an off by 1 error on steroids, right? But we're an off by an arbitrary value of n, right?
Yeah.
But your suggestion there's a case we haven't covered, and I don't know if we want to do it now. Your suggestion that we should return those 2 slices as sort of exposed. That's exposed a bit more of the workings of it, so we were able to validate that more easily, right?
Yeah, true.
And that's made it clearer. I think that we can sort of rework some of this so in our write case where we go, oh, well, this fits in the buffer, just write it in. Otherwise, put that little bit in, then write the rest. We could make that into a recursive call. So you write the end bit, and then you call back into yourself with the remaining stuff, and then that naturally comes into the upper branch.
That's
right?
Nice.
And then we'd need to move where we do our write to the output, but we could make that recursive. And I think we could do a similar thing with a look back. So you would kind of adjust the offsets to give you that. So where we're doing the second part, the second element in that tuple we're returning, you would call back, you would recurse back in there. I think the case we're missing at the moment, because we adjusted our test to accommodate this, the case we're missing at the moment is when the thing we write is too large.
Yes, I agree.
When we write a thing which is already much bigger than the buffer. So I think we can sort that really, really easily. So I would like to go to bed. I would like to do that and then go to bed.
Yeah, I like that.
So I think we can have a look back case again, but we put that string back together. So I don't know if you want to keep that like this, or you just want to reinstate that first.
I want both because I'm really not confident there. So this is going to be look back after overflow from several small writes, and this is look back after overflow from a big write. Really, we should do a small dinner big or something, but...
Yeah, but if you might remember that quite a long time ago now, I said half of me wanted to write this a byte at a time. And if we'd done that, some of these problems would have been easier, but it would have been horribly inefficient, right?
Yeah.
But that's, in a way, I have done that because that's exactly what I did in the bit iterator. I leaned on the iterator part is already giving us one read at a time, and I just lent on that to do the read. Now I'm we've been hoisted very firmly by my own petard by going, oh no, well that would be horribly inefficient, because I was quite happy to do it in a different circumstance in a different part of the same code base.
But
right.
So
this is going to fail.
Okay.
Because we're not accounting for the fact that
it passed.
I don't believe it. I don't believe that.
It's definitely more than 16. So the question is, what's happening? I'm worried that it's blowing the buffer, that it's making the buffer bigger, but the buffer length is 16. So let's look at write and figure out why it works. We're taking a large buffer. Oh, hold on. I think it's just, it doesn't fit. So we make the buffer the maximum size. Then we copy from buff, the beginning of buff, up to distance to end.
Yes.
So that distance to end is...
So we're truncating
the size, right, of the... Distance to end is the size, because the start index is 0. So this should be taking the first bit of buff and putting it in there. But is it then saving itself by doing this bit right?
That's weird, isn't it? Okay, make it even. We need to make it even bigger.
Yeah, because this is not big enough, because it's somehow...
It's not big enough. It's accidentally coming right.
It's jumping off those 4 bytes, and it's sticking them at the end.
Yeah.
No. Wait.
Because because it still fits.
Yeah, but it's putting the wrong bytes in, so how is this working?
This is working by mistake. I think we need to make effort. I think we make it even bigger. It will start to. By even bigger, I mean maybe a handful of bytes.
So, but my problem is I can't understand why it's giving us the right answer, because these 4 bytes surely got written at the beginning of the buffer. If I'm reading that code right, so how are they coming back to us? Or because start index got set to the beginning.
Hang on, out with 10.
I tell you what, we can break this by looking back further, I reckon.
You can't look back 16 because that's too many.
I can look back at 16, can't I?
Yeah, okay.
No, that'll be in 2 slices possibly, but... Will this work?
I don't know.
Have we accidentally done it correctly? Yeah, it's working. I mean, we've overwritten. All right, so you're right that if we do it from a, let's say from a meter.
Do it again.
So let's make it really big, because I think that will blow it. But I think the situation is that what we've done is overwritten 4 bytes wastefully, but actually come out with the right outcome.
I hate that I can't do the math for this in my head. Put some stuff in at the beginning of that string.
Let's put another 10 in, another 20 in.
Let's try that.
Yay. So there is something wrong.
Okay, right. So the fix, the correct way to handle this is to, at the start of write, if buff size is greater than self size, then we just take the last, just take size, the last size elements of buffer.
If buff len is greater than self.size, we do one thing. Otherwise, cache buff is going to be the same as buff.
Yeah.
And it's going to be some kind of start to the end.
And the start is buff len minus self size.
Yeah. And then everywhere we use buff, it needs to be cache buff.
Yes. Do not touch any. Don't stop. Come back up. Just change the input, change the name of the parameter. Lovely.
Ah.
Oh my God.
Sometimes.
Right, and then we let buff equal, and this becomes input buff.
Yeah, that was a good call.
Buff, and again in the if condition there in the let's start. What a magnificent advert we are for pairing, Andy.
Yeah, I mean, whenever I code, I'm a really good advert for pairing.
It's,
Okay, so the medium has changed its answer, but maybe still is correct. I don't know.
I don't know either.
So let's have a look at that one first. So 2, 4, 3. So it's come out as. It's come out all in one, I think.
Oh yes, it will now, and those others will come out as one as well.
What?
So if you run that now, this second test will fail. Yeah. So hang on,
because this is too many characters. It should be.
We haven't. Yeah. So it's 16. We're going back 16.
Yes,
so we need to go 1, 2.
It's wrong. It's giving us back the wrong answer.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It should be, 4, 5, 6, 7, 8, 9, yeah.
But it's not. It's coming out as just these ones. Because whatever we were doing that made us accidentally right, we're now accidentally wrong because we fixed that other thing. That's what's happening, because in write, we were writing all the bytes and then overwriting some of them.
Mm-hmm.
Now we've got the right length of buffer. We can't do that anymore.
Okay. Hold on. Up. Stop. If buffer len is less than or equal to distance to end, surely.
But that won't.
Yeah.
That won't fix it though, right? I agree that that's probably correct. It doesn't change anything. The problem is, in this second half of the if, we were getting away with it because we were copying the wrong bit of buff. We were starting at the wrong place in buff.
Okay.
because we were copying. We're starting from the beginning of buff.
Oh yes, okay. So now we want to so the end now. So start is from the start index, and end is size minus start.
But that
because we want to, we're doing that same thing. So so now we've aligned things properly, and so the bit that goes from start to end of the buffer is the start to that. Yeah, well, end is always going to be no, because we're going from yes. So that's now start. So this one is 0 to end. So it's not end; it's length.
Where? What?
Sorry. So the amount we want to copy is size minus start. So yes, yeah. Right, and then
I'm worried that this was the correct. This was these slices were the same size.
This is correct, right? And now the remaining buffer is length ...
And what did I press? Okay. I mean, that, at least keeping those consistent is right, but that's not fixed the problem.
Curiously, it's come out the same though.
Yeah, and it hasn't crashed. I was worried that it's going to crash because these things are different lengths from each other now. The two halves of this line 120. So I think what we've done keeps the same meaning we had before. We definitely want to start copying over at start index, surely, right?
Yes.
Buffer is the size of size at this point. Are we sure of that? No, we're not sure.
Yes. Oh no. Okay.
Yeah, that's the problem. We were assuming buffer is the size of size, but it may not be. We may just be overflowing a little bit, and buffer may still be quite small. It's just that there's not much room to the end of size.
Mm-hmm.
So that means we shouldn't be copying from.
No, hold on. Stop. When did this problem arise? When we tried to truncate the buffer.
Yes.
When I foolishly said this is an easy fix. If we go back to our examples where we're writing it and we're overflowing it in little steps, those are still working, right?
Yeah, only the medium right, which does overflow, and the big right are failing. Yes.
Okay, but the several small rights is working correctly.
Yeah, although we may not have done enough. But
so it's in the bit above.
Right, makes sense. It's big. Keep
going. It's here. It's this bit.
Is it? Start should be size back from the end of input buff. That sounds right.
Hmm. Can we Why do we have to have why have you written that it's a reference to the slice?
This is how you slice.
Or is that just what it has to be?
Yeah, you have to have an ampersand if you're slicing.
Okay, that's fine.
So buff.len is going to be size in this case. Distance to end is going to be less than size. So we're going to end up in this second half. So buff is the end of what we're writing. And in these big cases, the length of buff is exactly size. So that means we're not going to add anything to buffer here. This is going to do nothing. We have a start index which is partway in. No, the start index is 0. Start index is 0 in these cases, right? We're just doing one big write. So we should always be returning. So we should just be writing buff directly into. So we should just be doing this bit and then stopping. Like, we don't need this second half.
I think we might have. Okay. When the incoming buffer is bigger than. Oh, no, forget it. No, I'm talking nonsense. Fine.
So I just added in a debug about the remaining buff length. And in the big case, the remaining buff is 16 as I expected. In the medium one, remaining buff length is 4. But
which is right.
But I just said, like, in these cases, there shouldn't be anything more to write. Like, start index is 0. We should have just written everything into thing, and there should be nothing remaining. This buff. Oh, let's debug some more stuff. Do you see what I mean? Like, we should have just dealt with everything here.
But we shouldn't, in these cases, we shouldn't even have hit this branch.
No, we should have hit this branch, but...
Why?
That's interesting.
Oh. Size is wrong in our if statement. It's not size, is it? It's. Yes. Okay.
Why is
I've got confused about size and length. Size is always the capacity, right? It's always like 16 or whatever we set it to. Okay. Yeah.
So that's right, isn't it?
Okay. Yeah.
Okay, buff is wrong. So you're right. You're right that it's this code that is wrong. Let's write out what buff.len is. Oh no, it should be less than or equal to self.size. I'm talking rubbish. It's probably fine. No, yeah, it was fine. Ignore me. Okay, so thinking about the medium case, buff.length is 16 once, and then it comes in again, and buff.length is 4. Why are we hitting that line twice? This seems to be why we're having a problem. Have I messed up the test?
I don't know. Let's have a look.
We're in right. We're only doing one right.
It does look like it.
But hold on. But probably you could have multiple rights. But then, like, that could, the macro or whatever could break this up, maybe. But that seems unlikely.
Okay, well, can we just inline it then? We just call write directly?
We can, but, like, even then I don't know. It just seems really unlikely. Like, it seems like...
What do we get from our... if we scroll up a little bit, what do we get from our big write?
it gets called twice with 16 and 16.
So the right macro is getting in our way here.
Do you think that's what it is? Oh, fine. All right. There's sufficient doubt about it that we should call it directly.
It's curious that it's 16. Is the right macro looking at the size of the underlying, is interrogating the underlying writable to see what its capacity is and then writing that many bytes to it?
No.
No?
I would really be surprised. But you never know. Is it getting late?
It is getting late.
We should call write all. Right, then it will write all of them. Otherwise, write will just write some and then tell you how many it wrote. But this will call write multiple times.
Oh, I see. Okay.
So, like, no, let's just call write directly and assert that the answer is 16. No, not 16. Like, whatever it should be, 20. Right, we implemented write. It should do it all in one go. It shouldn't, like, tell you that it only needs some of it. Hang on, are we returning the right answer?
We need to change the right call at the bottom to input buff.
Yes, no wonder we were so confused. That's what it is. I'm so glad we found that because that was so confusing.
So now, right, yeah, okay. Yeah, so now we can do that, yeah.
Okay. Okay, so maybe the second half is now the right answer or something like that. Which ones are failing? So medium is failing at 252. So I'm just wondering whether this is happening now and whether that's fine.
Yeah, and then the next one will be, it will fail because it's all coming out in one piece now. Yes.
Right, is that good?
And that is correct. Yes, so because and that should come out on the left hand side. Yes, that's correct, and that's correct.
Okay, medium passed.
And it's the same with the big right because it's now coming out. Because that start is now right up there.
Yeah. Because once you've got a big buff, you just blank everything and set start index to 0.
In this case, because this is the first right and we filled it, start is now here. So when we do our look back, everything is to the right hand side, so it comes out in that one lump. But then for the other things where we don't wrap over, it all comes out on the left hand side. For some reason, my fans have started going. My old Mac is getting very excited now.
All I testified saying, all of our viewers have died.
All our viewers have died. So the right macro was doing a funny thing because we were misreporting the number of bytes we'd written.
And actually, it was really weird because we had actually written them into our buffer, but we said we hadn't. So then we got given them again. That was just crazy.
And then because our internal state had changed, eventually we did get into the right branch. But then everything was not where we expected it to be, so our comparisons were failing because all our offsets were now screwed up.
Yeah, because we were getting.
And if we jiggled it, and if we'd gone, oh yeah, that's an expected failure, and just adjusted our test output, we would have still ended up comparing the right bits of the same sequences, but they would have been wrong, and then we would have. We had a lucky escape. Oh, Andy, I'm So sorry, mate. I thought this was going to be a super quick one.
Well, I'm sorry.
This turned into the longest one ever.
I mean, it's content. Like, you should be grateful, viewer. I mean, there's like one viewer left, but they are loving this.
And yes, if you're affected by any of the issues raised in this video,
join the club, mate.
Support is available from.
Okay, so we're not going to do it now because we've done enough.
No, God, no. We're not going to. We're just going to commit this now.
But
turn the lights off.
What this deserves is to talk through the implementations of both write and look back, and
yes,
probably refactor them so that they're much easier to read. But we're not doing that now.
Yes. No, we're not going to do that now. I will pick that up, and I will write this up as a supplementary thing, like I did after the bit iterator.
That is so awesome. Like, you doing that makes it feel like a real thing. It's amazing.
And we can and hopefully that'll make it clear, because some of this, because this is kind of fascinating for me, right? Because if I was doing this at work, if I was having to do Rust at work, like, for example, I'd suddenly got a job at Element and I was having to write Rust all the time.
Element's currently looking for Rust engineers.
Yeah, that was very good. That was your feed line for that. Then, do you know what I mean? The whole of this would have been compressed into about a week. Mm-hmm. You know what I mean? And you'd have got used to the code base and the idioms and the standard library facilities that we're using in a particular code base you were working in, and you'd be probably pretty comfortable within a few days, right? And I've done this lots and lots and lots of times with lots and lots and lots of different languages, like, I don't know, like 30 different languages over the course of however long it is, right? Mm-hmm. I've had a very weird career, Andy. But here, because we do this in kind of little, kind of intense bursts that are spread out over time, it doesn't stick in the same way. So going back and looking at it again and reworking and doing that refactoring step that we haven't really done here helps consolidate that stuff. So that when I do go back, like I did when I did my little cell implementation, I got really, really handy with iterators because it's all iterator based, right? Yeah. And the new thing that I've just started and I've written approximately 15 lines of, by the time I've done a bit more of that, I'm going to be your Rust process control wizard, right? Because it's going to be all that stuff. But this, where we're doing different bits and we're doing like wacky stuff, copying stuff in and out of vectors.
Yeah. And to be fair,
it's all new.
To be fair, it was right there for the taking that we could have just used a vec deck and this would have been done for us.
Yeah. But this, and also it's kind of quite a common problem.
Yeah.
And it would have been easy just to go, oh, let's find a circular buffer crate. Yeah. It would have been fine. All right.
That would have been the fun.
But it would have been less fun, I think.
Yeah, but I really...
Yeah, but that's, again, if I was at work, if this was a work thing, absolutely I would have reached that circular buffer, right?
Yeah.
I don't, the whole implement a linked list thing. I don't know if people still do that in job interviews, but like I would refuse to do that because I'm never going to write you a linked list, right?
Yeah.
I don't think I've ever needed to use one. I've never had the right use case for it. But almost certainly. But you would go to your library, right?
Yeah. But
because that's the sensible and pragmatic thing to do for the thing that you're doing for work. Yeah. And this is quite clearly not work.
However much work it might feel to watch, it's not work for us to record these videos. But I really feel like I really want this, because it is a common problem. there should be language and ways of writing this code that makes it clear, maybe not completely trivial, but clearer than it is in my mind at the moment.
Yes. And I know what you mean.
Thank goodness for tests.
Yeah. There's a more expressive Rust that we haven't found yet.
Mm-hmm. Mm-hmm.
I don't mean we, the two of us.
Yeah.
But I think I mean we collectively, because a lot of the Rust you see is very. It's a lot of words.
Yeah, and there's a lot of noise inherent in some.
And there's. I don't know. I used to find when I worked in my brief foray into Ruby that a lot of Ruby is written with the methods tend to be very long,
right,
and very nested, because you'll do something like people will write a for each, or you call each on a container, right? Mm-hmm. And that you pass in a code block, which is a lambda effectively, and people will inline the lambda.
Just don't do it.
But the lambda gets progressively bigger and bigger and bigger. Yeah. And it's not the kind of, it didn't seem to be, it might be different now since I've done this, but people wouldn't lift that lambda out and give it a name. Right. They just so if you had a thing that did it looped on something 3 times, you'd end up with a chunk and a chunk and a chunk and a method that was this long.
Yeah.
And I feel like a lot of Rust is like that, especially when you get those let expressions.
Right.
You get let if. Yeah. And if there's a let if inside the if, and then a let if inside the if, do you know what I mean? Suddenly,
and then
you've written 12 lines just to initialize a variable.
Yeah. So there are rare occasions where you can't factor things out into a function because the buttons don't work. But those are so rare that you can't blame them. It's a cultural thing. And
I've certainly encountered that situation where you say, well, if you try and extract it, suddenly you get caught up in the types just don't fit.
Which is
you've got you want to do an early escape in one case, and you can't do it if you put another scope around. Yes,
and I think, there are also situations where the LSP actually could extract a function for you if it was better at its job, which hopefully will come. But there are times where the types actually seem to block it from happening.
It's that early escape particularly, but they just there doesn't seem to be, and it's just only my impression, there isn't a culture of brevity. Do you know? There's a.
I don't know about that. So I definitely think there's a culture of, yes, this is hard. I only do hard things, right? And that can lead to a culture of a lack of brevity, because you're not actually looking to make it look simple if you have that attitude.
Yes, and we all know where that leads, right?
Yeah.
Lisp. If ever a language didn't have a culture of brevity.
Yeah. So I think that you can write clear and readable Rust, but I do, especially in tests, I find myself ploughing through long old tests with a load of setup and stuff, and it could have just gone into a function with a name that described it. That irritates me. But you can do it, and I do work with people who especially some who really go for expressive, and maybe go too far because they then write macros that are really expressive, and you have no idea how they work.
Yes,
well, that's a separate problem.
Yeah, we'll work it out.
We will. So long as we stay in our little bubble of writing everything by hand, and we'll make progress slowly and surely.
Well, Rust is, in the grand scheme of things, still a young language.
Oh yeah,
right?
Yeah, and even that control flow stuff. Like, we should really go to bed. But anyway, there are these control flow things you can return from functions which don't do anything yet. It's just like control flow : break, and then you have to match on that if you want to break on it. But there is talk of making that into something that is obeyed in some way, and then maybe some of that early return will work out.
Go away. Yeah.
And async feels like it was thrown together and still needs a lot of thinking, and there is some talk of progress on that.
I think even without language changes, it can take a long time to really find, just to kind of find the heart of the language itself.
Yes, and when I think about exception safe C++, for example, how long it took to understand that. Yeah.
And that was at least 10 years.
Yeah.
After, probably longer.
I think it was 20 years after exceptions.
Yeah, I think that's fair. After that, initial article. And so,
Oh, no, I didn't mean, I didn't mean after the article. I meant after exceptions. It was at least 20 years since exceptions were invented.
Oh.
Yeah.
Yes. Yeah. But yes, the idea. Yeah. So, many more hours to come, viewers.
So many, like, will we ever decompress anything that's been compressed? Nobody knows. Well, I will catch up with this. I'll try and do that in a relatively timely way. I'll shut up now. This was awesome. Thank you, Andy. Yeah, like, if you go on too long, you get tired, and then you can't stop talking. And I think that's where we're at.
Yeah, I'm afraid we might be. Yes, so I'll just
fizzle out about here.
If you got this far, do email in.
Leave a comment on the blog. That's where the cool kids are commenting on these videos on my blog at artificialworlds.net/blog. Thanks a lot. So, if you made it, you are incredible, and see you next time.
Bye-bye, friends.